Hello and welcome. In this video, we'll walk through a proof for a classic inequality. By the end of this lesson, you will be able to apply two powerful techniques, the Cauchy Schwarz inequality in its angle form and the AMGM inequality, to construct a rigorous mathematical proof. Our goal is to prove that for any positive numbers a, b, and c, the expression a squared over b plus c plus b squared over c plus a plus c squared over a plus b is always greater than or equal to a plus b plus c, all divided by 2. Let's first take a moment to look at this inequality. We have a sum of three fractions on the left and a simple average on the right. This type of structure often suggests using the angle form of the Cauchy Schwarz inequality, which is a powerful tool for these kinds of problems. Before we dive in, let's quickly review the tool we're about to use. This will help you understand the next steps clearly. The Cauchy Schwarz inequality in its angle form, sometimes called the T2's lemma or T2's theorem, states the following. For positive numbers x sub 1 through x sub n, and positive numbers y sub 1 through y sub n, the sum from k equals 1 to n of x sub k squared over y sub k is greater than or equal to the square of the sum of the xk's, all divided by the sum of the y sub k's. In simpler terms, the sum of squares over variables is greater than or equal to the square of the sum over the sum of the variables. This is a very useful formula for summing fractions with squares in the numerator. Now, let's see how we can apply this directly to our problem. Notice how the left-hand side of the inequality we want to prove matches the form of T2's lemma. We can identify our terms. Let x sub 1 be a, x sub 2 be b, and x sub 3 be c. And let y sub 1 be b plus c, y sub 2 be c plus a, and y sub 3 be a plus b. By making this correspondence, we can apply the inequality. Plugging these values into T2's lemma, we get that our original left-hand side, a squared over b plus c and so on, is greater than or equal to the quantity a plus b plus c squared, divided by the quantity b plus c plus a plus b. This simplifies our problem greatly. We've replaced a complex sum of fractions with a single, simpler fraction. Our proof now depends on this new expression. So, we've shown that our original left-hand side is greater than or equal to this new fraction. Let's call the original left-hand side L. We have established that L is greater than or equal to a plus b plus c squared over the sum of b plus c, c plus a, and a plus b. Let's simplify the denominator of this fraction. The denominator is b plus c plus a plus b. Rearranging the terms, we have 2 a's, 2 b's, and 2 c's. Factoring out a 2 gives us 2 times a plus b plus c. This is a nice simplification. Now we can substitute this back into our inequality. We have that L is greater than or equal to a plus b plus c squared over 2 times a plus b plus c. Since a, b, and c are positive, their sum is also positive. So, we can safely cancel one of the factors of a plus b plus c from the numerator and denominator. This leaves us with L is greater than or equal to a plus b plus c divided by 2. Let's compare this to our original goal. This is exactly what we wanted to prove. So, by applying T2's lemma directly, we have proven the inequality. We've shown that the left-hand side is greater than or equal to the expression on the right. That was one direct and elegant way to solve this using T2's lemma. But what if you weren't familiar with that specific inequality? Let's explore a second method, a more traditional approach, that proves the same result. This will reinforce your understanding of powerful algebraic techniques. The second method we'll use is the Arithmetic Mean-Geometric Mean inequality, or AMGM. AMGM states that for any non-negative numbers, the arithmetic mean is always greater than or equal to the geometric mean. For two numbers x and y, this means x plus y over 2 is greater than or equal to the square root of x times y. Let's apply AMGM to the first term of our inequality, a squared over b plus c. We'll apply AMGM to the terms a squared over b plus c and b plus c, all divided by 4. This might seem like an arbitrary choice, but it's a common trick to make the denominator cancel out. the sum of these two terms over 2 is greater than or equal to their geometric mean. Notice the beautiful cancellation on the right side. The b plus c in the numerator and denominator cancel each other out, leaving us with a squared over 4. The square root of this is a over 2, so we get that half of our sum is greater than or equal to a over 2. Multiplying by 2 on both sides, we get our first AMGM inequality. A squared over b plus c plus b plus c over 4 is greater than or equal to a. This provides a lower bound for our first term. That was a great first step. Now, we repeat this process for the other two terms in our inequality. This technique is often referred to as slicing the inequality. Applying the exact same logic, we can say that b squared over c plus a over 4 is greater than or equal to b. And similarly for the third term, we find that c squared over a plus b over 4 is greater than or equal to c. Now we have three separate inequalities. We have the inequality for a, the inequality for b, and the inequality for c. Our next step is to combine these three results. By adding these three inequalities together, the sum on the left-hand side will still be greater than or equal to the sum on the right-hand side. Let's perform this addition. On the left, we add all three left-hand sides. On the right, we add all three right-hand sides, which just gives us a plus b plus c. We are now very close to our target inequality. Our final step is to simplify the left-hand side of our combined inequality and then isolate our target expression. Let's focus on the second part of the left-hand side, the sum of the three fractions with denominator 4. Since these fractions all have the same denominator, we can combine their numerators. Adding the numerators, we get b plus c plus a plus b. Just like before, this simplifies to 2 times the quantity a plus b plus c. Dividing by 4, we are left with a plus b plus c all over 2. Now let's substitute this simplified expression back into our main inequality. The first part of the left side is our original expression. The second part, which we just simplified, is a plus b plus c over 2, and this whole sum is greater than or equal to a plus b plus c. To get our final result, we simply subtract a plus b plus c over 2 from both sides of the inequality. This gives us a squared over b squared over c plus c squared over a plus b is greater than or equal to a plus b plus c minus a plus b plus c over 2. This simplifies to a plus b plus c over 2. And with that, we have successfully proven the inequality using the AMGM method as well. We've shown the same result through a different but equally valid path. So, we have now seen two powerful methods for proving this inequality. Let's take a moment to recap what we've accomplished. Our objective was to prove the given inequality for positive numbers a, b, and c. The first method used the angle form of the Cauchy Schwarz inequality. By correctly identifying the terms, we were able to simplify the left-hand side into a single fraction. After simplifying the denominator and canceling terms, the inequality followed directly and elegantly. The second method used the AMGM inequality in a technique called slicing. We split the left-hand side into 3 terms and applied AMGM to each one individually, adding a strategic term to facilitate cancellation. By summing the resulting 3 inequalities and simplifying, we arrived at the same conclusion. Both methods demonstrate how choosing the right tool can make a complex problem much more manageable. You can now confidently apply both T2's lemma and the AMGM inequality, which are essential techniques for solving a wide range of inequality problems. Thank you for watching.